嘅問題先係最大問題，到出咗問題先嚟解決問題，所有問題係自己問題，檢查一下唔可以喂，有乜冬瓜豆腐就冇眼睇，留意安全冇分高矮大細，你隻眼開隻眼閉就閉翳，揾個註冊人士嚟睇睇，有石屎剝落好大劑，亂個搏叫佢講危唔危？個窗框會唔會跌落嚟？為你僭建物就唔好制。喂，嗱，check 樓，喂，等到出咗問題先嚟解決問題。喂，嗱，check 樓，快解決問題，做得靚仔仔。喂，嗱，check 樓，樂園安全，開心用一世。喂，嗱，check 樓，喂，check 樓，嘅問題先係最大問題。先嚟解決問題，所有問題係自己問題，查一下唔可以喂。Body check。
Good afternoon. Welcome to the third briefing session on Code of Practice on Wind Effects in Hong Kong 2019. I'm Fiona Au, Technical Secretary of Substructural of the Buildings Department. The Code of Practice on Wind Effects in Hong Kong 2019 has been issued for nearly 17 months. I guess most of you have already go through the details of the code. It helps industry to estimate the building response and estimate wind loading more accurately. To help the industry to understand more about new features of the code, Buildings Department organized 2 briefing sections last year, one in January and one in September. Today is the third briefing section in English. Similar to the previous ones, Engineer Alexis Lee of Arup will introduce the new features of the 2019 code in the first part. And then Dr. Leptun Yu of Arup will introduce how to use the code with some examples. Then we'll have a 15 minutes break, followed by Q&A sections. If you have any questions on the new code, please press the live event Q&A at the top of the screen and type in your questions. We will answer those questions with the highest hit rate. Lastly, after the briefing session today, we will upload part 1 and part 2 of today's briefing section to the BD website so that you and your friends can review it at any time convenient. Okay, let's get started. Alexis, thank you.
And good afternoon, everybody, and welcome to the second online briefing section of the Hong Kong Wind Code 2019. Today's content mainly divided into 3 parts. The first part is the key update from the 2004 to 2019. The second part is the demonstration of the case example, and then we'll go into the Q&A section. So from the key update, the first thing we need to consider the application or the applicability of the new code. First step is to verify whether the standard approach is acceptable or not. There are 3 major criteria. First of all, whether the building height is less than 200 meters, whether it is an unusual shape, and whether it is located on a complicated topographic location. And if any of the answer is no, then the standard approach does not apply and wind tunnel shall be conducted. And among all the 3 criteria, the 200-meter limit is the criteria newly added to the new code. Code-based wind design covers 2 categories of design, which is the old design of the overall building structures and the design of cladding or building elements. For building design, it includes the calculation of structural wind load for stability, capacity, and deformation calculations. And it also includes the calculation of wind-induced acceleration response for human comfort. And the work procedure can be found in Figure 2-1 of the new code. For building elements, a similar equation as for the calculation of the building elements can be found in the code for capacity and deformation check, and also the workflows can be found in Figure 2-2. Now we go into the major wind design of the building. To start, we have a comparison of the flow chart of the two between the two codes. On the left-hand side is the same work flowcharts based on the 2019 format. And you can see they are very similar. And within that, the orange and pink components are actual old contents. The green are newly added contents. The red fonts within the boxes are actually content being updated. As a key point to note, the key component of the 2019 code are very similar to that of the 2004. First of all, you need to calculate the along wind component, and then you calculate the crosswind and torsional component. And with all the components calculated, then you can work out the load combination for the overall load effect. In the old 2004 code, to calculate the along wind calculation, there are two approaches. One is the static approach, which is more suitable for short and stocky buildings. And then for tall and slender flexible building, you will adopt the dynamic approach. But in the 2019 code, we have simplified the calculation method to just one unified approach. For detailed content, in the 2019 code, there are two newly added components to the design wind pressure, which is the directionality and also the sheltering effect. And it will be explained in the upcoming two slides. For consideration of directionality, the directional factors in the key direction are given in table A-1-1 of the new code. And directional factor between two nearby key directions can be obtained by interpolation. For consideration of the sheltering, we'll demonstrate it with a simple example now, and it will be further discussed and explained in the section 2 or in the part 2 of this presentation. For the case one here, without sheltering, a building of 200 meters, if you want to work out the design pressure at a reference height of 150, and you can get the pressure value strictly from the table 3-1, which is 3.05. If the same building is now situated in a dense urban area with sheltering from the upwind direction, you may imagine that the wind pressure being uplifted to a certain height. For example, in this particular case, if you assume the displacement height of 50 meters, your effective reference height EZ will equal to 150 meters minus 50 meters. So your new reference pressure are reduced from 3.05 to 2.68. In addition to the new contents, there are new components which has been updated, which is the force coefficient and the size and dynamic factor. For the force coefficient, in 2004 core practice, it can be calculated based on table D1 and D2. In 2019, it has given a more appropriate update based on the latest research. You can see the graph on the right-hand side. And also in the code, you have given a formula-based CF, so it can be easily applied for special calculation. In 2019 code, it also provides guidance on considering the aerodynamic benefit from the corner modification, such as due to chamfer or corner resection in equation 4-2, and that also from the round corner in equation 4-3. Definition of B and D for irregular shape is often a complicated matter. In the new code, it provides a further guidance on defining the equivalent rectangle for several common and non-standard plan shape in order to better calculate the force coefficient. And for the update on the dynamic factor, and you can see in the old code 2004, it's relatively complicated. You have 7 equations to work on. And now in the 2019, we have taken considerable effort to simplify the procedure. And the equations are now given on the right-hand side. After we calculating the along wind, now we need to formulate a crosswind and torsional load component. In the old 2004 code, in clause 7.6, it stated that if the crosswind restaurant component response is significant, then such effect should be considered in the calculation. But it didn't give a very it didn't specifically give an assessment method beyond an internal test approach. In 2019, we now have introduced a new equation to calculate the torsional load and also the crosswind wind load equation. And in the next 2 slides, and we will give you the explanation. First of all, the crosswind wind load formula. The crosswind-based moment formula is given in equation 2-2 of the code. It is related with the damping ratio, lateral frequency, building geometry information, and also the wind profile. And for the torsional component, it is generated by cross 2.2.2. It is to generate an equivalent torsion by applying an eccentric lateral load. The load eccentricity is related to the B and D ratio of the building. The bigger the ratio, the bigger the eccentricity to apply. And after we got the force component, then we can now use the load combination in the new code to calculate the overall effect. In the old 2004, you need to calculate the 2 orthogonal direction and also then the diagonal component of the wind load. In the 2019, this is simplified as such that you only need to calculate the 2 orthogonal direction and applying the combination in table 2-1 to work out enveloping all the load combination cases. Now, after you calculate that, then regarding whether you still need to go for internal test, initially, the first criteria is to check if the building is less than 200 meters. If it is yes, then you go for the codified approach. But however, it is still need to verify whether the wind resonance dynamic effect is significant. And in the 2004, it has not been quantified. And in 2019, the criteria have been set between the ratio of the crosswind moment and the along wind moment. If the ratio is less than 1.5, or the other way around, if the ratio is greater than 1.5, then you need to proceed with the internal test. As shown in the slide above, the wind direction 1, you can work out the M along wind based on the codified equation. And then based on the wind direction 2, you also work out M across base moment. Based on the ratio of the 2, if it is greater than 1.5, then you will need to go for internal test. And this is similar to the 2004 criteria, but the 2004 have not been quantitatively explicitly stating the criteria, and you just need to go for the literature research based on the literature, the specific literature. And in 2019, the code also provided a codified method to calculate the building acceleration for human comfort. This new equation, acceleration assessment criteria, is also included a new assessment criteria, which is frequency dependent and which is also more scientific and is based on the latest research. The 2000 code incorporated the hoarding and cover walk weight in the PINAP into the code of practice, and it's also further expanded it for some simple temporary structures such as bamboo shed, tent, and marquee for the non-residential purpose. And for damping, in the 2004 code, 2 constant value or damping ratio is given in the code for two material, which is the steel and concrete, and is not distinguished the damping ratio for structural wind load or for human comfort. In the 2019 code, we provide more clear guidance or the recommendation of the damping ratio based on building material and the aspect ratio. And it also provides 2 sets of damping ratio for calculating of the structural wind load and one for the comfort. The 2019 code also gives recommendation on how to generate the critical load case for multiple towers sitting on a common podium. It includes rules for translation governance loads case and also for the torsional load case. And the detail of the recommendation are given in E2 and E3 of the explanatory note of the 2019 code for references. Now we come to the second part of the update, which is on the cladding wind load. In 2004 wind code, the wind pressure can be worked out, or the wind pressure can be worked out based on the wind profile if the building height is greater than the building width. In the new code, the 2019, the QH, which is the reference, is the pressure reference, is now based on the building top, which is taken rather than following the approach wind profile. And the background of this is because the distribution of the peak pressure suction does not follow the approach profile, and this is also been proven through scientific research. And lately in the ASCE, the BSCN, and also the New Zealand Cook, Japanese Cook, Korean Cook, all have taken this as the reference. The second major update in the wind pressure coefficient, the wind pressure assessment for the cladding, is the size factor. In 2019 code, we have taken into account the influence of the loading area of peak pressure by adopting this size factor. So it's also related to the location and the size. And the same concept is already adopted in the ASCE and the BSCN as well. The 2019 code gives guidance for the force coefficient of small building attachments, such as sunshade, architectural fin, and signboards. And it also gives guidance on the pressure coefficient of freestanding walls. Another key feature update in the wind cladding element is 2019 code provide more specific guideline on the extent of the edge zone in the irregular geometry such as Z, L, and T. Now we come to the final part of the first update presentation, is relating with the wind tunnel test. In the new 2009 code, there are 4 major guidance given in the code for the wind tunnel test. The first of all is the quantitative guidance for the wind tunnel test if it is required under clause 2.2.3. And then there is a specific guidance on the requirement on the topographic model and the positivity model, which is under clause 6.1.3 and 6.1.4. And after that, also in the appendix of the core practice A2, and you can find specific guideline of the removal of the sheltering obstructions. And last but not least, the lower bound guidance is also given in the clause 6.4. The old code 2.4, and you need to carry out the internal test based on the existing configuration, removal configuration, and also compare with in the code along with. And in the 2019, if you do the same approach, then you will allow it to have a bigger reduction in loading, which is 20% of the wind removal case. Then you will take the envelope of the free configuration. However, it also allow you not to carry out the removal case. You can just simply do the existing case and then you compare with the wind code. Last but not least, 2019 code, if you follow the procedure in the code, then you will not require to carry out a SC meeting for the internal test for the method statement in the approval stage. I think this covers all the points I would like to bring for the update in the key update in the key content. And now I will pass to my colleague Lap Thuen to explain with some work examples. And thank you.
Okay, thank you, Alexis, for the introduction. Following what explained by Alexis on the general rules, so here I would like to supplement with the actual working example. So for this working example, I'm going to present three parts. One is a general rule for shattering effect calculation. And after that, it will be two specific working examples. One is a shorter building with the L shape, and another one is a taller building about 190 meters. So that is mainly to introduce about the a crosswind calculation and also how to do the scale up and also the related wind tunnel testing judgment and criteria. So here, let's go through the general rule on sheltering effect calculation first. For the sheltering effect, as explained by Alexis, it can achieve some benefit on reduced reference wind pressure. For example, as the example explained, originally without any sheltered building, then we are going to evaluate the cladding, the reference wind pressure at 150 meters. Then the pressure will be 3.05 kilopascal. But now, because of some upwind obstructing building, the wind profile is lifted upward. So then the effective height for evaluating the pressure is only 100. So then there is a reduced wind pressure from 3.05 into 2.86 kilopascal. So that is the benefit. So then here, the key is how can we determine the displacement height? So this is the so-called uplift of the approaching wind profile. Within the code in Appendix A, so the displacement height are governed by three formulas. So that related to the height of a particular obstructing building. So the taller the building, the taller the obstructing building, the bigger the sheltering effect. Also related to the distance between the obstructed building to the target building. So the bigger the distance, the smaller the sheltering effect. And the third part is a lower cutoff limit to restrain that the benefit cannot be too over. So next, I'm going to present some general rules regarding the sheltering effect calculation. Number one is if there is only one obstructing building, for example, as what is shown in the screen, so then no shattering effect should be taken. Number two is if there are more than one obstructing buildings, so then the shattering effect of each building, obstructing building, shall be calculated. For example, we calculate all the building obstructing buildings, their shattering effect one by one. So here in figure 8.82.3, there is a counter plot. Within this counter plot, the ratio between the obstructing building height over the target building height, that's the horizontal axis, and the ratio between the distance between the obstructing building over to the target building over the height of the target building, that's the vertical axis. So for each of the three buildings shown in the screen, we can evaluate their shattering effect. So then after the evaluation, we see the middle taller building that gives the biggest shattering effect. So for this one, following the rule, we should ignore its effect. So then we need to go through the second most benefit building. So that is the slightly shorter building, but closer to the target building height. So that provides the second biggest shattering effect. That shall be taken for the final calculation. And the third rule is for buildings in the same building lot, they shall be treated as a whole when evaluate the direct shattering. For example, if any building within the building lot, they are identified as the most beneficial building, they shall be removed. So the principle behind is for buildings within the same building lot, in case of a future redevelopment, the case all the buildings within the lot are redeveloped or demolished are very high. So that's why we say when we considering the most sheltering building and to ignore that beneficiary effect, the buildings in the same building lot, they should be treated as a whole. Next are some specific rules how to considering sheltering effect in slope terrain conditions, because all their introduction before are considering a flat terrain. So in case of slope terrain, the evaluation of sheltering effect shall be taken from a slightly more conservative perspective. To give an actual example, so in front of the screen, we can see it's a hill slope, and the black building is a target building. It is located on top of the hill, and in front of the target building, there are several obstructing buildings. The wind is blowing from the bottom to the top of the hill. For this, we can have two considerations. So one is to assume the wind blows in a direction in parallel of the hill slope. So if considering that, the obstructing building height will be the same as the actual building height. And the second one is if we assume the wind blows horizontally. So in that case, the obstructing building height will be shorter or smaller than the actual building height. So following the rule that we are going to take the more conservative approach, so then what we are going to do is when we calculate the actual obstructing height of the sheltered of the obstructing buildings, so we should take the base level of the target building as the reference level. So then the obstructing building height will become a reduced obstructing building height as highlighted in blue, rather than their actual building height as highlighted in red. So that's for the case with the wind blowing from the bottom to the top. The second case is the target building is located at the bottom of the hill, and there are also some obstructing building on the slope of the hill, and the wind blows from the top of the hill to the bottom. In this case, also we can have two consideration how the wind will approach. One is if the wind approach in parallel as the slope of the hill, so then the sheltering or obstructing building height will be the same as actual building height. And another one is if we assume the wind approach in the purely horizontal direction, so then for the obstructing building close to the top of the buildings, their sheltering effect will be bigger than their actual height. So still following the rule that we shall take the sheltering effect from a slightly more conservative perspective. So for wind blow from the top to the bottom where the target building is located, we take the actual building height as their obstructing building height. So this is how the sheltering effect shall be assessed for a slope terrain condition. We discussed before is assuming it's a one-dimensional problem. So that means wind blow just from the side to a far direction. But actually, wind blow is in a two-dimensional. So that means it's not only from the side to a further distance, but also across some horizontal distance, left and right to the side. There are also some variation. So then the further rule is sheltering effect shall be evaluated for all the four orthogonal directions, each covering about 90 degrees. So this is to say, for a site to be assessed, if it is a two-dimensional problem, so we should divide the site into 4 quadrants. So each or 4 quarters, each cover about 90 degrees. And for each of the 90 degrees, we are going to investigate if there are more than one obstructing building or surrounding building, which with the height varied across a sector or across the 90 degree. So then the displacement height, which is HD, should be taken as the weighted average value about all those obstructing calculated HD values. So here is an example. So on the side for one direction, so we consider about plus and minus 45 degrees, so that is totally 90 degrees. And then across the 90 degrees, we can see there are 3 obstructing buildings. They have a different height. So then we identify for this, we can further divide into 4 divisions. So for each division, we can calculate the displacement height HDI. So then they need to be weighted average about the angular length, which can be covered. So that is the finally obtained displacement height value for this 90 degrees should be a weighted average value across the whole 90 degrees. So some tips to be shared is one is the 90 degrees can normally be equally divided into no more than 4 divisions, not fewer than 4 divisions, and each 90 degree can also So also more equal divisions normally lead to easier calculation, because for smaller divisions or cover smaller angular length, it is easier for one building to occupy the whole division. So that means we need fewer effort to consider the weighted average. So that is why we say that will lead to a slightly easier calculation. So that's the general rule for the shattering effect calculation. And I think later in the actual working example, we can go to some more specific details about in actual condition how this rule shall be applied. So we go to working example 1. For this first working example, we are studying a 90 meters tall building. The height is about 90 meters, and the horizontal plane is an L shape. And the breadth is about 40. And for this L shape, the two wings, about the depth is about 15 and 25 meters, respectively. The building is located in a town center, so you can see there are lots of other buildings of a similar height densely located around our target building. And for the natural frequency, we use the rule of thumb of 46/h. So that gives us about 0.51 Hz for both directions. The objective of the case study. So the first objective is that we want to introduce the general workflow, how to use the 2019 code. So for example, at the very beginning, we need to make judgments whether a wind tunnel testing will be needed or whether the standard approach can be applied. So if the standard approach applies, we can go downward to calculate a long wind load. For the along wind loads, so it will have 3 components. So one is a design reference wind pressure, and the force coefficient, and the size and dynamic factor. So for the design reference wind pressure, it also related to directionality, sheltering, and topographic effect. And then after that, we need to make a judgment whether a crosswind effect is significant or not. After that, after the consider of a crosswind, so we can calculate the torsional load, a long wind load, and a crosswind load. So then we do the load combination. Another key point we want to highlight is a special feature of this case is so we intentionally select a short building. So for this case, we also demonstrate that for which when particular conditions are satisfied, actually the crosswind checking doesn't need to be applied. So the long wind will govern automatically. And another point we highlight is from this working example, we give a detailed example about how to calculate the shattering effect. So here we go through the steps one by one. The first step is initial judgment, whether codified or standard approach applies or not. So that we need to consider the total building height, which is about 90 meters, and it's okay. So it's shorter than 200 meters, and it is a Euro shape, and it is not located in either a complicated surrounding or a complicated topographic condition. So all the criteria are satisfied, then the standard approach applies. So then for following the standard approach, the first step is to determine the design wind pressure. This building is aligned north and south, so it's as what is shown here. So the first we consider the directionality. In the table A1/1 of the Appendix A of the 2019 code, the directionality factors for the 8 key directions has been provided. So we just plot them, and then for any further directions falling between the 2 nearby key directions, we just do interpolation. So here we give a particular example if wind blow to the WX1 minus direction. So then we first define the one of the 4 orthogonal directions. So that is to start about at the east direction plus and minus 45 degrees. So that's the two, starting from the 2 corners. That's the 2 red dashed lines. So for that, we can see it covers about 3 directions. That is east, southeast, and northeast, which gives the directionality factor of 0.85, 85, and 84. So we pick up the biggest one among the 3, so that is 0.85. So that's the directionality factor for wind blows in WX1 minus. So following the similar rule, so the directionality factor for all the other 3 orthogonal directions can be calculated. So as listed in the table, which are 0.84, 0.85, and 0.84. After the calculation of the directionality factor, we are going to consider the shattering effect. As explained before, this target building is located in a dense urban center, and all the surrounded buildings, they are of a similar height and very close. So because of that, the simplified shattering calculation approach can be applied. So the detailed procedure is in the appendix A 1.2 of the EN. For the detailed procedure, what we are going to do is first we consider a radius. So within this radius, we are going to consider the shattering effect. Beyond that, so the shattering benefit will be ignored. So this radius is taken as the smaller one as 500 meters and the 6th time of the target building height. So here the 6th time of the target building height will be about 540. So the smaller one is about 500. So the radius is drawn as 500. Further on that, we divide the plan into 4 sectors, each cover about 90 degrees. So as shown in the 4 quarters divided by the boundary line of the green lines. So then for each of the selected 90-degree sector, we further equally divided them into equal divisions. So the interval is 10 degrees, so totally we have 9 divisions. And then in the radial direction, so for easier reference, we further draw some further mark. The interval is selected as a 0.5 h. H is the set building height. So this is easily for us to do any quick calculation. So we can see the mark is a 0.5 h, 1, 1.5, 2, and 2.5 h. So next is we are going to start to calculate the shattering effect. So as shown in the simplified approach, within the radius of 2 times of h, so this is here. For all the buildings which are taller than 90% of h, so 90% of h, so the h is about 90 meters, so this is about 81. So any buildings within the 2 times of h and taller than 90% of the height, not taller than 81 meters, they will be given as HD over H as a 0.7, as highlight and as shaded in the red color. Right. So the next one is for any building which are within the distance of 2 times of h. So this is the 2 times of h, and this is the 2.5 times of h within this area. So we give any obstructing building height which are taller than 90 meters, give HD over H as a 0.7. So for our case, we don't have that. And within the same range, for any building which are taller than 0.9 H, So that is about 81 meters. We give them as HD over H as 0.6. So those are the building as shaded in green color. So those displacement height will be the HD over H equals to 0.6. Then we are going to pick up which are the first beneficial building. So those buildings will be, the sheltering effect from those buildings will be ignored. Because the red color and the blue color, they are all buildings which can give the biggest or maximum sheltering effect. So for easier selection, we just pick up the first row. So that is from Tower 1 to Tower 5. So they are selected as the most beneficial building, so as highlighted, as shaded in red color. And those 5 buildings, they covered all the 9 divisions. So after that, we are going to identify the second most beneficial building. So the first most beneficial building has been highlighted in red box. So the second most beneficial building are going to be selected from the remaining buildings. So first, to pick up Tower 6 to Tower 8, so this also gives the full sheltering of a 0.7 H as a displacement height, and they cover division from 1 to 3. And then we pick up Tower 9 and Tower 10. They also give a full sheltering that cover division 6. Further, we pick up Tower 11 to 14. So that is shaded in the green box. So that cover division 4, 5, and 7. The displacement height is about 0.6. And finally, conservatively, we consider division 8 and 9. There's no further obstructing building after the first beneficial building is removed. So that taken displacement height as 0. So with all this calculated, so we do a weighted average. In total, in all the 9 divisions, we have 4 divisions have a full sheltering that is the 0.7, 3 divisions with the displacement height as a 0.6, and 2 divisions with the displacement height as a 0. So after doing this weighted average, we can calculate the displacement height is about 0.51. And then the sheltering, the effective height will be about, so the displacement height will be 0.51 multiplied by 90 meters. So that is 45.9 meter. That's the displacement height. Following the same rule for all the 4 directions. So the effective height ratio, HE over H, can be calculated for all the 4 quarters. So here we pick one of the 4 directions as an example to do the further calculation. So we pick up the WX1 meters. That gives the displacement height about 40. So that gives the displacement height about 45.9 meters. And then the reference wind pressure is given in equation 3.2, the topographic factor, because here we are assuming it is located in a flat terrain, so that taken as 1. So then this table lists all the calculation procedure. So first we have effective height. For this effective height, we shall be careful that for the Z level bigger than 1.33 of displacement height. So that is 1.33 of displacement height, which is 45.9, and the final result is 61.2. So anything above 61.2, we take the ZE effective height is equal to actual height minus displacement height. But anything below 61.2, so the this effective height ZE should be taken as 0.25 as EZ. So that is highlighted as in the blue box. So you can see in the blue box, it is not HZ minus HT anymore. It is 0.25 EZ. So after the EZE effective height is calculated, the QZ flight, the reference wind pressure can be calculated in the QZ flight, and then following the following what is introduced before, topographic factor is taken as 1 because it is located in the flat terrain. Finally, the QEZ can be calculated based on equation 3.1. So that includes directionality factor, the shattering effect, and also the topographic factor. After the reference wind pressure is ready, we can go further for the calculation of the long wind force. Within this, we need to further identify the force coefficient. The force coefficient is related to the geometry of the tower and also related to whether shattering effect is taken. So for this, we have we have wind blows from the x1 minus direction. So the projecting breadth is 25 meters. That's the breadth. And for the depth, following the figure 4.4e in the COP. So the depth should be the average between the two depths on the two sides. So then it is the average between 40 and 10. So that is 25. That's the D. And for this case, if we look at the force coefficient graph, it's also related to the H over D, but it's not H. It's effective building height. It's HE over D. HE in our case is 44, which is not 90 meters. 90 is the original building height, but the effective building height is only 44, 44.1. So HE over D is about 1.76. The B over D is 1. So by using the two figures, we can look up the actual force coefficient on the force coefficient graph. Within this, the force coefficient is calculated as 1.17. After the force coefficient is calculated, we further calculate the size and dynamic factor. For the size and dynamic factor, we need to identify the size factor using the building breadth. So that is in the equation C1/1A. So that is based on the breadth of the building. So after the size factor is calculated, we go to the equation 4.1. That is to calculate the size and dynamic factor at the top of the building. For this factor, it's related to the geometry, it's related to the natural frequency, and also related to the damping ratio. With all those bring in, we can calculate the size and dynamic factor at the building top as 1.04. And then further following the equation in 5.2, so we can calculate the size and dynamic factor for all the building height. So this is also listed in the table below. That varies from 0.67 at the bottom to 1.04. So with all those parameters ready and calculated, finally using the equation 2.1, so we bring in the reference wind pressure, the force coefficient, size and dynamic factor, bring everything. We can calculate the wind load at each level. So then we do a summation. We can calculate the shear force and the bending moment at each level. So here at the base, we calculate the base shear as 4 meganewton and the base moment as a 199 meganewton meter. So this need to be recorded because later we also need to compare against the crosswind-based moment to see whether adjustment is needed or wind tunnel testing is needed. Further on this, we can keep calculating the torsional force. The calculation of torsional force, as explained in Alexis' briefing session before, is relatively simple because we can just shift the lateral force with the eccentricity. The eccentricity is related to the planar dimension ratio, the B over D ratio. So for the x1 direction, the B over D is equal to 1. So the calculated eccentricity is about 0.05. And in the x2 direction, the B over D ratio is 2. So for this one, we can do an interpolation between 0.05 to 0.2. So 0.2 is about B over D equal to 6. So from this calculation, the eccentricity is about 0.08. That is for the x2 direction. And then the final equivalent torsion is equals to the lateral force multiplied by the shifted distance in that direction. So for all the 4 directions, we can calculate the 4 torsional force. So the reason why we have 4 results is because of the directionality and the shattering effect. So for this, finally, the finally adopted torsion is the maximum among the 4. Next is the calculation of the crosswind load. For calculating the crosswind load, I think we also need to make a judgment whether the crosswind response is resonant response is significant or not. So if we look at the flow chart, actually, it is as shaded in blue color. So there are 3 criteria. So one is whether the building height is shorter than 100 meters. In our case, yes, because we are only 90. And the second one is whether the 2 slenderness ratio in 2 directions are smaller than 5. In our case, also yes, because it's 4.5. And the third criteria is whether the natural frequency in both directions are higher than 0.5 hertz. The answer is also yes. So with all the 3 criteria satisfied, there's no need to further check the crosswind-based moment. So we can use the along wind force result to do the load count directly. Then it's a load combination. So we have got the along with the lateral force in the 2 orthogonal directions. We also get the torsional force. So following the load combination table in the table 2.1, so we can do the load combination directly. The last step is the checking of the acceleration. For checking the acceleration, we assume the tower density is mass density is about 300 kilogram per meter square. And the calculated with all those parameters bring in equation 2/4, the 1-year acceleration is about 0.024 meter square. And if we look at the acceptance criteria, because the natural frequency is about 0.5 hertz, so we look at the acceptance criteria. Even for the most stringent residential tower, it is about 0.05 meter per second square. So that means our calculated acceleration is far below the acceptance criteria. So we pass the human comfort check. And further we go have a look at the cladding pressure. The cladding calculation is relatively straightforward. We can follow the equation 2.3a. Within this, we assume the cladding panel size about 1 meter by 1 meter. So then the half parameter length is about 2 meters. And following the figure 5.4, for the edge zone and for the other zones, we are talking about the wall elevation. For the edge zone, the size factor is calculated as 1.22. And for the non-edge zone, the size factor is calculated as 1.09. And with the size factor and pressure, and the reference wind pressure, as discussed before, need to be taken as top of the building. So then for direction WX2, so this is calculated as 2.13. And the pressure coefficient for the positive pressure coefficient everywhere, it is 1.1. And for the negative pressure coefficient, it is minus 1.4 for edge zones and minus 1 for the non-edge zones. And one point need to be further highlighted is according to the code, for a location or for the level which are within the 0.5 of displacement height. So within this case, the 50% of the displacement height is about 55.75 meter. So within this range, the calculated wind pressure can be reduced by about 20%. So then with all those included, we can calculate the cladding pressure value. So on the elevation, there are two zones. So one is above 15.75, so that is above the half of displacement height. So we can have one set of cladding value, and below that we can have a further 20% reduction. So this is the calculation of all the cladding pressure result. And this is the end of example 1. For working example 2, so this is a tall building with a building height about 195 meters. And the plan shape is a rectangle, but it also have some recessed corners. For the plan dimensions, it is about 62.5 in one direction and 39 in the other direction. The objective of the study is one, to introduce the corner modification, and another one is to introduce the calculation of a crosswind-based moment. Further is to consider the scaling up of a long wind after comparison of a crosswind. And last is to introduce how we consider when a wind tunnel test will be needed. So still the first step is the judgment of whether a standard approach applies or not. So still the 3 criteria all satisfied. Okay, so the codified approach applies, no need for wind tunnel test. The second one is the determination of a design wind pressure. For this one, the general principle is exactly the same as the last working example. The only difference is that in the previous working example, the tower is aligned south or north. For this one, it is not exactly aligned south or north, but it doesn't matter. So we can divide the 4 quadrants as highlighted in 4 different colors, and for each color for each quadrant, we can still use the the directionality factor for the 8 key directions and do an interpolation with anything in between the 2 key directions. And finally, we can identify the directionality factors for all the 4 orthogonal directions, as shown in the table. After that is a determination of the design wind pressure. For this case, we assume the tower is located in a blank area, a blank site. So there's no surrounding the building to provide shattering effect. So the effective height is equal, ZE is equal to Z. And we also assume the tower is located in a flat terrain. So the topographic factor is also equal to 1. So then following equation 3.1, the reference wind pressure can be calculated along the tower height. Then the calculation of the along wind force. The calculation of along wind force, we need to calculate the slenderness ratio and the B over D ratio. For this case, because there's no shattering effect, so HE is equal to H. So HD over H is 5, and B over D is 1.61. So if we look at the figure, the graph, we can calculate the force coefficient is about 1.37. And another point we especially want to highlight in this case is actually we have a recessed corner. Following the rule in the code, in equation 4.2, for recessed corner case, we can have a further reduction on the force coefficient. By calculation, the reduction factor is about 0.97. So then the final force coefficient is 1.37 multiplied by 0.97, so it's about 1.33. So again, we need to identify the size and dynamic factor. So by using the building breadth, we can calculate the size factor as 0.91, and using the natural frequency, damping ratio, the geometry information, we can calculate the size and dynamic factor at top of the building as 1.08. Finally, using equation 5.2, we can calculate the size and dynamic factor along the building height. Then we can calculate the along wind force along the whole building height. And finally, we can calculate the base shear and base moment, especially for the base moment, that is 3,569. So this is important because it's especially for this case, finally we need to compare the along wind base moment and the crosswind base moment to consider whether any further adjustment is needed or whether wind tunnel testing is needed. For the torsional force calculation, which is the same as the last time, for the two directions, the eccentricity is about 0.05 for x1 and 0.068 for the x2 direction. Then the torsional force is picked up as the bigger one of the two orthogonal directions, as highlighted in blue. Next is the calculation of the crosswind base moment. Still, we need to go through an initial judgment about whether the crosswind base moment is significant. Also, three criteria. So the first one is whether the building is shorter than 100. So we are not, because we are 195. So that means the crosswind base moment may be significant. We need to use the codified formula to do the calculation. What we need is that we need to follow the equation 2.2. Within this, the crosswind base moment is related to the peak factor gamma Ry. So that is related to the natural frequency in the direction of the crosswind load direction. So this is calculated as 3.5 in our case. And the load factor taken as 1.4, natural frequency 0.25. And turbulence tested at the top of building, that is 0.096. Then the damping ratio for the WX2 direction is about 3%. So with all those bring in, we can calculate the crosswind base moment for the WX2 direction, for wind blow to the WX2 direction, that is 17559. So then following the same principle for all the four directions, we can calculate this as respectively for the along wind-based moment and a crosswind-based moment for all those directions. So take Wx1, so the black arrow, wind blow from left, as an example. So the along wind-based moment is a 1757, so that's in orange, single direction. And the crosswind-based moment is a 2432. That is in blue, that is bidirectional, because a crosswind moment is bidirectional. And for wind blow from Wx1 minus, the same. For wind blow from Wx2 minus, so that's from the top to the bottom, a long wind-based moment is a 3569, that's orange, single direction. And for the a crosswind-based moment, that is a 1759, bidirectional. So we can do this for all the 4 directions. So then finally, we need to make a judgment, first of all, whether a wind tunnel test will be needed. For this, for the vertical direction, so as shown in the purple arrow, so in the vertical direction, we pick up the bigger crosswind, so that is the 2432 and 2581 as highlighted, underlined in green. And also we, in the same loading direction, so that is very important, for the same loading direction, we pick up the biggest along wind-based moment. So that's the bigger one between 3569 and 3569. So the ratio between the two is 0.7. It's smaller than 1.5. For the horizontal direction, we do the same. So then the ratio is a 0.97. So still smaller than 1.5. That means no direction we have the ratio bigger than 1.5. That means we don't need to conduct a wind tunnel test. The codified approach still applies. So next one is, do we need to do any scaling up for the along wind? So here it seems for the horizontal direction, this is closer to 1. So we further check. For the horizontal direction, the crosswind moment is a 1759. And for the along wind moment is a 1757. So very close to 1. So we don't need to do further adjustment. So this is the end of this particular case. And in order to introduce some further variation or different scenario, we reduce the natural frequency in x1 direction slightly. So originally it's a 0.25 hertz. So now we make it more flexible. So the natural frequency drops to 0.21. So then here we can see, because of this change, the along wind-based moment increased slightly. But the increase of the crosswind-based moment is even bigger, more obvious. So still, we do the same comparison. For the vertical direction, everything is not changed because the natural frequency doesn't change, so it's the same. For the horizontal direction, we pick up the bigger one for the new crosswind-based moment, so that is 2.2175, and the bigger one of the new along wind-based moment, so that is 1873. So the ratio is 1.16, still smaller than 1.5. So that means still we don't need to do the wind tunnel test. However, so be careful here. Do we need to do any scale up? Yes, because for this direction, for the original along wind-based moment 1837, it has been smaller than 2. For the crosswind-based moment 2175. So it needs to be scaled up. The scaling up factor is about 1.16. And for the original crosswind-based moment 1.07, it also need to be scaled up. The scaling up factor is a 1.21. So this is the case 2A. We don't need to do the wind tunnel test, but the along wind-based moment in the horizontal direction need to be scaled up in order to match the crosswind-based moment. So case 2B is if we further make it more flexible in the x1 direction, so that means we reduce the natural frequency into 0.15 Hertz. So then the crosswind-based moment will increase substantially into 3272. Although the long wind-based moment also increase, but with a smaller percentage of increase. For this case, for the x2 direction, so we can see the bigger of the crosswind-based moment has already been 3272, and the bigger long wind moment is 2022. The ratio between the two is now 1.6. It has been bigger than 1.5. So then, in this case, we need to do a wind tunnel test. The codified approach doesn't apply. So any codified calculation need to stop. We need to do the wind tunnel testing result to further complete the wind-related design. So those are three variations. So let's assume we use the original case. So that is, we don't need to do the wind tunnel test. So then, after the two orthogonal lateral force in the two orthogonal direction and the torsional force, then we can do the low combination following the low combination factor. Again, we can check the acceleration. Assuming the tower density, mass density is 300, the calculated acceleration is about 0.032 meter per second square. And using the natural frequency of 0.25, we can find the acceptable limit is about 7.07. So still, again, we are far below the acceptable criteria. So we are okay, pass the acceleration check. So finally, it's a very quick and simple calculation of cladding pressure. We assume the cladding panel size is about 2.5 by 2.5. So the size factor for the X zone and for the other zone are respectively 1.12 and 1.05. And we use the top of the building as a reference height. So the reference wind pressure is 2.71. And then the calculated cladding pressure are respectively listed in this table. So that's all for the calculation of the working example. So I think also this is all the contents of the presentation contents today. So please stay online. So there will be a short break for 15 minutes. So after that, we can have a Q&A session. So we welcome you have all your queries or questions, so then we can have a more fruitful discussion. Thank you.
Hey. Yeah. What? Woo! Mic check. Take check. Take a check. Mic check. Take check. Take a check. Dolly check.乜嘢問題先係最大問題？都出咗問題先嚟解決問題。所有問題係你自己問題。檢查一下唔可以喂。有乜冬瓜豆腐就冇眼睇，樓宇安全冇分高矮大細。你隻眼開隻眼閉就閉翳，揾個註冊人士嚟睇。有石屎剝落好大劑，亂咁落條佢講危唔危？個窗框會唔會跌落嚟？違例僭建物就唔好制。喂，嗱，赤樓，喂，等到出咗問題先嚟解決問題。喂，嗱，赤樓，快解決問題，做得靚仔。喂，嗱，赤樓，樓宇安全，開心用一世。喂，嗱，赤樓，先係最大問題。先嚟解決問題，所有問題係你自己問題，檢查一下唔可以喂。Body check。 就冇眼睇，樓宇安全冇分高矮大細，你隻眼開隻眼閉就閉翳，揾個註冊人士嚟睇睇，有石屎剝落好大劑，亂咁撲掉佢講危危，個窗框會唔會跌落嚟？為你錢見物就唔好制，喂，赤佬佬，喂等到出咗問題先嚟解決問題，喂赤佬佬，快解決問題做得靚仔仔，喂赤佬佬，喂。赤佬佬，喂等到出咗問題先嚟解決問題，喂赤佬佬，快解決問題做得靚仔仔，喂赤佬佬，安全開開心心用一世，喂赤佬佬，赤佬佬，赤佬乜嘢問題？或是係最大問題？就係到出咗問題，先嚟解決問題。少問題，大問題，喂赤佬佬，問題先係最大問題，到出咗問題先嚟解決問題，所有問題係自己問題，檢查一下唔可以喂，有乜冬瓜豆腐就冇眼睇，樓宇安全冇分高矮大細，你隻眼開隻眼閉就揾個註冊人士嚟睇睇，有石屎剝落好大劑，亂個撲掉佢講危危，個窗框會唔會跌落嚟？為你錢見物就唔好制，喂赤佬佬，喂等到出咗問題先嚟解決問題，喂赤佬佬，快解決問題做得靚仔仔，喂赤佬佬，樓宇安全開開心心用一世，喂赤佬佬，赤佬佬，咩問題先係最大問題？到出咗問題先嚟解決問題。所有問題係你自己問題，檢查一下唔可以喂。Body check， 有乜冬瓜豆腐就冇眼睇，樓宇安全冇分高矮大細，你隻眼開隻眼閉就閉翳，揾個註冊人士嚟睇睇。有石屎剝落好大劑，亂咁撲掉佢講危危，個窗框會唔會跌落嚟？為你錢見物就唔好制，喂赤佬佬，喂等到出咗問題先嚟解決問題，喂赤佬佬，快解決問題做得靚仔仔，喂赤佬佬。赤佬佬，喂等到出咗問題先嚟解決問題，喂赤佬佬，快解決問題做得靚仔仔，喂赤佬佬，樓宇安全開開心心用一世，喂赤佬佬，赤佬佬，赤佬佬，乜嘢問題？或是係最大問題？就係到出咗問題，先嚟解決問題。少問題，大問題，喂赤佬佬。 Mic check, tick check, take a check. Mic check, tick check, take a check， 多啲 check， 多啲 check。乜嘢問題先係最大問題？當出咗問題先嚟解決問題。所有問題係你自己問題。調查一下唔可以喂。有乜冬瓜豆腐就冇眼睇，樓宇安全冇分高矮大細。你隻眼開隻眼閉就閉翳，揾個註冊人士嚟睇睇。有石屎剝落好大劑，亂咁撲叫佢講危唔危？個窗框會唔會跌落嚟？為你閃電物就唔好制。喂，嗱，check 樓，喂，等到出咗問題先嚟解決問題。喂，嗱，check 樓，快解決問題，做得靚仔。喂，嗱，check 樓，樓宇安全，開心用一世。喂，嗱，check 樓，check 樓，乜嘢問題先係最大問題？先嚟解決問題，所有問題係你自己問題。調查一下唔可以喂。Body check， 多啲 check。有乜冬瓜豆腐就冇眼睇，樓宇安全冇分高矮大細。你隻眼開隻眼閉就閉翳，揾個註冊人士嚟睇睇。有石屎剝落好大劑，亂咁撲叫佢講危唔危？個窗框會唔會跌落嚟？為你閃電物就唔好制。喂，嗱，check 樓，喂，等到出咗問題先嚟解決問題。喂，嗱，check 樓，快解決問題，做得靚仔。喂，嗱，check 樓，check 樓，喂，等到出咗問題先嚟解決問題。喂，嗱，check 樓，快解決問題，做得靚仔。喂，check 樓，樓宇安全，開心用一世。喂，嗱，check 樓，check 樓，乜嘢問題？先係最大問題，就係到出咗問題先嚟解決問題。少問題，大問題。喂，嗱，check 樓。就冇眼睇，樓宇安全冇分高矮大細。你隻眼開隻眼閉就閉翳，揾個註冊人士嚟睇睇。有石屎剝落好大劑，亂咁撲叫佢講危唔危？個窗框會唔會跌落嚟？為你閃電物就唔好制。喂，嗱，check 樓，喂，等到出咗問題先嚟解決問題。喂，嗱，check 樓，快解決問題，做得靚仔。喂，嗱，check 樓，樓宇安全，開心用一世。喂，嗱，check 樓，check 樓，先係最大問題，出咗問題先嚟解決問題，所有問題係你自己問題，調查一下唔可以喂。Body check， 多啲 check， 有乜冬瓜豆腐就冇眼睇，樓宇安全冇分高矮大細，你隻眼開隻眼閉就閉翳，揾個註冊人士嚟睇睇。有石屎剝落好大劑，亂咁撲叫佢講危唔危？個窗框會唔會跌落嚟？ 為你千千萬就唔好制。喂，嗱，check 樓，咪等到出咗問題先嚟解決問題。喂，嗱，check 樓，快解決問題，做得靚仔。喂，嗱，check 樓。check 樓，咪等到出咗問題先嚟解決問題。喂，嗱，check 樓，快解決問題，做得靚仔。喂，嗱，check 樓，要安全，開心用一世。喂，嗱，check 樓，check 樓，乜嘢問題？先係最大問題，就係到出咗問題，先嚟解決問題。就冇眼睇，樓宇安全冇分高矮大細，你隻眼開隻眼閉就閉翳，揾個註冊人士嚟睇睇，有石屎剝落好大劑，亂咁撲叫佢講危唔危？個窗框會唔會跌落嚟？為你千萬就唔好制。喂，嗱，check 樓，咪等到出咗問題先嚟解決問題。喂，嗱，check 樓，快解決問題，做得靚仔。喂，嗱，check 樓，要安全，開心用一世。喂，嗱，check 樓，check 樓，先係最大問題，出咗問題先嚟解決問題，所有問題係你自己問題，調查一下唔可以喂。Body check， 有乜冬瓜豆腐就冇眼睇，樓宇安全冇分高矮大細，你隻眼開隻眼閉就閉翳，揾個註冊人士嚟睇睇，有石屎剝落好大劑，亂咁撲叫佢講危唔危？個窗框會唔會跌落嚟？為你千萬就唔好制。喂，嗱，check 樓，咪等到出咗問題先嚟。
Hello, welcome back. Thank you for staying with us. Here's the Q&A section. So we received quite a lot of questions here, and we are happy to have Leslie and Neptune Yu here to answer the questions. So the most popular question is, please explain how to calculate the wind load on Podium, which is shared by Twin Towers. So may I invite Dr. Neptune Yu to answer this question?
Okay. For this one, actually, we have a recommendation in the EN. So in the EN, it's Appendix E. So can we show? Okay. So in the Appendix E, so for this multi-tower sitting on podium, so generally it's a talk about if we have several towers, so they share the same podium. For this case, so if there is no moving joint, how we can make sure that the critical load cases for designing the podium can be covered. So here I just talk about the general principle. So the details we can refer to the Appendix E in the EN. So the general principle is for the tower design and for the, especially for the podium design and for the foundation design, we need to make sure that we can cover the most global critical translational load case and the global torsional load case. So for the global translational load case, within the Appendix E, so actually we further explain, so the whole plan can be divided into 8 divisions. So then for each tower and for the podium, we need to pick up 1 vector. So then with all the towers vector wind load summed together, we can generate the biggest translational load. And this is for one division. And for all the 8 divisions, if we follow the same principle, so we can cover all the translational critical load case. And for the torsional load case, so what we need to do is based on the picked up for the biggest translational load case, so we know for each of the 8 divisions, which is the most critical load. So then we give a rule to apply an equivalent eccentricity, so that can generate an equivalent torsional load. That aerodynamic will be something similar to the torsional load generated by partial wind load on the towers. So then with the partial load on the towers together, we can generate all the torsional governed load case for the podium and for the foundation. So that's the general rule. And in the end, I want to further explain, for the twin towers, the condition will be slightly simple compared with the multi-towers case. Because for the twin towers, we have only 2 towers. So for the critical torsional case generated by the partial load on the towers, we can consider 1 tower is fully loaded and the other one is unloaded. So that will make the total load cases fewer, so less than the multi-tower case. So for more details, please refer to the appendix in the EN. Phil, that's my answer.
Yes.
Or maybe can I supplement a little bit on here? Because twin tower is a very special case. Actually, there are special literature out there you can find. And if you have specific sort of requests or using beneficial of using those literature, I'm sure we can discuss those in the technical section meetings.
Yes. Okay. Thank you. And then the next question is, do we have the presentation already on the BD website? Yes. Sorry, we haven't uploaded the previous presentation on the website yet. But after the webinar today, we will upload today's part 1 and part 2 to the website. So stay tuned to our BD websites, and we'll have some pop-up news later. Okay, the third one is okay. So the next question is, if a building was designed to 2019 code according to the wind tunnel test results, but during the construction, the clients would like to have a signboard attached to the building, is it required to carry out the wind tunnel test again to justify the wind load on the building for any such building attachment not foreseeable in the early design stage? Actually, this question is applicable to the current 2004 code. So if a wind tunnel test is conducted based on an early design stage model, and in case that during the construction stage or afterwards, the building owner want to add some attachment, or even they change the building height, the wind tunnel test the wind tunnel test laboratory can carry out a test study to assess the effects of the change in the building shape and some maybe some addition of some building form. So and to assess and to recalculate the wind tunnel test result such that the design can incorporate such change. Yeah. So any supplement? If no, then okay. The next question is, when can those building heights be obtained from the government source? Okay. Actually, in the lands department, there are many maps available in digital formats. In this map, you can actually know the coordinates and the building heights and building shape of these buildings. So we welcome the industry designer to use this map to calculate the sheltering effects on the proposed building of your project. So of course, other than the lands departments, if the designer has other source of building heights, actually we will consider the relevance and reliability of these source and maybe use in the design. But at the moment, I think the map from the lands department is the most reliable source for us. Okay, the next one is, can we use wind tunnel test to determine the design wind pressure for building elements such as cladding? Are there any requirements in the code? So I think, Lepton, can you answer this question?
Okay. So I think here I want to clarify that the wind tunnel testing can cover both the structure wind load and also the cladding wind load. So definitely we can conduct the cladding test to instrument the surface wind pressure on the entire building. So that is for building envelope design. So that also includes for any attachment, so which the designer or the client, they want to get more accurate wind load. And for particular guidance, how to conduct the wind tunnel testing, particularly for the cladding design, I think we also have very specific rules in the chapter 6 of the code of practice. So please refer to the more details there. So that to summarize, I think the answer is very clear. Yes, that can be used for wind tunnel test for cladding design. Yeah.
Yes, actually currently we accept both wind tunnel tests based on force balance or to calculate the structural load and the building response of the structures. And also we accept pressure tap integration method so that the wind pressure of the building facade can be measured. Okay, so the next question is, in the 2019 code, is there any requirements on the channel down effects which similar to clause 6.2 of the 2004 code? So may I invite Lepton to answer this question as well?
Okay, so I think the so-called channel down effect is generally by the, if the wind flow hit on the building surface, so then there is a wash down and at the lower portion of the building surface. So the wind pressure will be higher than the approaching wind profile. I think that is why some of the audiences, they ask this question. So the answer is also clear, is yes. So in the 2019 code, actually, we have already increased the reference wind pressure. So from the actual level Z into the building top. So this increase, so one of the purpose is to cover the washdown effect. So the answer is yes, very clear.
Yes, so I would like to take this opportunity to remind designers that for building facade design such as curtain wall, window wall, remember, don't use the building pressure at the level of the building elements to use the design. Remember, use the building height, at the top of the building for the facade design. So you may refer to clause 4.3.1 to check the wind pressure, the height of the pressure. So if the building is the tower is set back from the podium, you can use the podium height for the facade of the podium. And then for the facade of the tower, you remember to use the tower building height at the top for the design.
Yeah, and Fion, I think I want to follow up what Fion mentioned. I think this time, so for the 2019 code, we have more clear and comprehensive guidance. So with the tower sitting on the podium, and also relative to the location, whether it's sitting immediately on the edge of the podium or so with a quite big setback. So I think all can refer to the clause 4.3.1, so for the two different categories and conditions.
Yes, thank you. So the next question is, as stated in clause 2.5, for hoarding and cover walkway and the like, 37% of the wind reference pressure could be used, but no other adjustment factor should be applied. So what is meant by the other adjustment factor? So the other adjustment factor actually means the further reduction by the directionality factor and the sheltering effects. So remember, these two factors actually 37% of the wind pressure is already a very big discount. So further discounts due to the directionality and the sheltering actually is not allowed in this case. But remember, you designer need to use the topographic factor and the size factor in this respect. Yes, okay, the next one. is do we need to consider wind loads in diagonal directions, such as UV? So may I invite Alexis to answer this question?
I think this is in the new code. This has been simplified in a way that in the old code, you need to design, calculate the two orthogonal direction force and also the two orthogonal direction force. But in the new code, you only need to calculate the two translation force and then use the table 2-1, the low combination factors, to calculate the overall wind forces from various directions. And that actually cover all the 8 directions or 24 locations in there already with the torsional component.
So may I interpret, actually the UV direction has been catered by using the low combination factor of 1 and 0.55.
Yes.
So so designer, remember that you use the local axis of B and D to find out the along wind and the crosswind moment and the torsion. Then actually you can use the low combination factor to take into account the diagonal wind direction.
Yeah. So the 24 locations actually are more comprehensive than the old code. So it covered the wind can blow from any directions. So that is to combine the 2 lateral force and two translational force and 1 torsional force.
Yes. Okay, thank you. So the next question is, if the proposed wind tunnel test methodology comply with all the requirements in the 2019 code, should we need to submit to the Structural Engineering Committee for consideration? Yes. So I think it's a good news for the industry that if you follow the chapter 6 of the 2019 code, the methodology proposal for the wind tunnel test actually is not necessary for the set case. But if some of the laboratory, they prefer to use other methods or on directionality or maybe other settings on the models, then maybe the proposal need to be go through the technical section and also the set case. So we strongly suggest you to use the wind tunnel test, to conduct the wind tunnel test according to the chapter 6 of the code. Yes, okay. The next one is for wind tunnel test without considering building removal configuration. Do we only consider 80% of the along wind loads from the code, or do we need to consider crosswind as well? Okay, may I invite Alexis to answer this one?
Yeah, if you refer to the flow chart in the code, you actually specified if you do without the removal configuration, the comparison lower bound is 80% of the codified wind load, which include both the maximum value between the crosswind and the long wind. So basically, it will cover the crosswind case in the assessment.
Yeah. So for this one, I want to further supplement a little bit. So if we do the removal configuration, so because in the wind tunnel we have a very comprehensive configuration. So that means for both configurations, if we need to use the lower cutoff value, that means a crosswind may not control. So that's why we cut off at a long wind. But for the only testing with the existing configuration, there may be a chance that for the removal configuration, the crosswind may govern. So if that is not tested, then we need to use the code to do a cutoff.
Yes. So for this question, remember that the 80% is to the codified value, which means a long wind and a crosswind has to be considered in this case. And also, I like to take this opportunity to remind you that the capping limits actually apply to the total base moment at the bottom, which means the 80% of the code is compared to the total base moment obtained from the wind tunnel test. So, and then the wind profile, how to spread up to the story loads, actually it should follow the wind tunnel test results, which means you obtain the scaling factor by using the total base moment and then apply this scaling factor up to the story load. So we don't want to change the wind tunnel test. Okay, I hope this answers your questions. Okay, the next one is how to calculate the torsional moment due to split diaphragm analysis. Actually, this is a quite a broad question because split diaphragm can be due to a number of various situations. But we confine this question to a scenario that the building actually behave aerodynamically as one building. But due to the structural design, or maybe due to some big voids within the buildings, designer has to they can't use rigid diaphragm for the wind loading design. And in that case, they need to use the split diaphragm. And then the question is how to calculate the wind load to simulate the torsional moment in this case. So may I invite Lepton to answer first?
Okay.
And then see Alexis has any supplement.
Okay. So I think thank you, Fion, for give a constraint or give a limitation. So for this topic, because as you mentioned, it's quite a broad topic. So following what Fion says, if we assume this is a scenario that aerodynamically, so even though we have two diaphragms or splitted diaphragm, but aerodynamically it is still a one tower. So for this case, so we can still use our code to calculate the overall wind load. So that is the overall lateral force and the overall torsional force. So then the next step is how we can generate a appropriate distribution about the wind load to the different diaphragms. So I think this need to a more careful consideration by the structure engineer and maybe with the assistant of a wind engineer. So then, but I think one general rule we can think about here is so this after the force ablation, the sum of the distributed force on diaphragm A and diaphragm B together need to generate the same total lateral force calculated by the code. And also the splitted or distributed wind force on diaphragm A and diaphragm B together should also be able to generate the equivalent torsion that is calculated based on the code. I think this is a general rule I think the user may be able to follow at this moment.
Okay, any supplement? No? Okay, thank you. So the next question is how to obtain the natural frequency for the building higher than 100 meters? Okay, Lepton, please.
So I think at the beginning of the code, so we gave the recommendation how to calculate the natural frequency. So normally it's two categories. So building shorter than 100 meters, we still follow the old rule of thumb. So that is the height over 46 over h. So that is for natural frequency calculation. But for building taller than 100 meters, so we have this time we have a more stringent requirement. So we require all the case need to go through the finite element analysis to get a more accurate natural frequency. So the reason is because in the 2019 wind code, we have the new provision for a crosswind-based moment.
Yes.
So this crosswind is quite dynamic and very sensitive to natural frequency. So we should have a more accurate estimation of natural dynamic properties, including the natural frequency, in order we can have an appropriate and a reasonable crosswind estimation. Yeah.
So can I say that they need to use some computer model to help them to estimate the first mass and the frequency at first.
The first
and then based on this assume or maybe the first draft of the frequency, they do the design. But in the future, maybe they need to readjust.
Yeah,
readjust the frequency and the mass and recalculate. We know if it's still within the design range.
Yeah, it's like an iteration. So they keep updating the finite element model and then they keep updating the wind load. So.
Actually, this situation is similar to the wind tunnel test at the present.
Yes.
For the wind tunnel test conducted nowadays, even for the 2004 code, they need to use the computer model to establish the mass and the natural frequency so that the wind tunnel laboratory can do the tests.
Yes.
But in the future, they need to readjust and reassess if the mass and the natural frequency are still applicable. Am I correct?
Yeah, especially for the natural frequency.
Yes. Okay. Thank you. Oh. Okay, it's fine.
Okay.
And then the next one is pressure coefficient CP of 2.0 for open frame structure in 2004 and sorry. Is it still valid for the new code? Yeah, it is. Actually, you may refer to clause 4.3.3 of the new code. Actually, the table of the open frame coefficient is still here. So you may refer to the code for details. But we also add some other coefficients, some more coefficient for other types of building elements, such as canopy and fins. So industry, the designers can use it with more ease. Okay, the next one is, okay, good question. Please compare the same building under the assessment of 2004 code and the new 2019 code. Which one is more adverse? Okay, may I invite Alexis?
I think, yeah, we did do a lot of comparison, but not with the same, not necessarily with the same building. We compare with a range of aspect ratio and also a number of configuration and locations, because when the building is located by the seaside and one's actually located in the urban dense area, you have a different characteristic subject to the wind condition. So for those, we have compared generally the 2019 code we think is more beneficial to use, and as a result of the new development in the research which we have incorporated into the code. Tim, maybe you want to add further?
Yeah. So following what Alexis introduced, I think together with the BD, I think, and also under the requirement of BD. So a very comprehensive parametric study has already been conducted. So that includes the different aspect ratio and also the sheltering conditions. It means whether it is on the seaside or in the suburban or even in a very dense urban center. So all those conditions and also the plan ratio, that B over D ratio, this parametric study has completed. So it's difficult to say, so which is higher, which is lower. So I think, and also I think the question is quite complicated. There is no uniform trend. But I think one thing, according to the study, is very clear is for this very slender building in the very exposed side, for example, in the seafront. So the 2019 code is expected to give a higher wind load because this is more scientific. If even you do the wind tunnel test, it will reflect the similar issue because the highly dynamic driven crosswind response has now been reflected in the new code. However, on the other side, on the other hand, if the building is located in the urban center and with all the surrounding building of a similar height, then the sheltering effect will provide a very big benefit. And if we take that into account, and especially if the building is not very slender, so more likely the 2019 code will give a smaller wind load. So I think both cases reflect a more scientific picture. So for the 2019 code.
Maybe I simply just add to that is that the 2019 code is more scientific and also giving a more procedural method to calculate a more realistic wind load based on the existing condition, which is just compare more advanced than the 2004.
Yes. Actually, during the consultation of the wind code, with the help of a number of RSCs during the consultation, we actually have some sensitivity analysis for a few cases, real projects. These real projects are designed to wind tunnel test results. So we have the wind tunnel test result and the building form. Actually, we carry out a study to estimate the wind load based on 2004 code, 2019 code, and then compare against with the wind tunnel test results. And the standard method for these cases, generally, actually, the results are close to the wind tunnel test results. And for most of them, as the wind loading from the 2019 code is actually smaller than the 2004 code because we introduced torsionality factor and shattering effect. So all these factors actually reduce the total wind loading. Yes, thank you for this question. And then the next one is about the fundamental frequency. The wind code 2019 calculations are based on fundamental frequency n, x, and y, which are aligned with a long wind and a crosswind direction. There may be some building forms where torsional frequency modes may dominate more than translational mode. Do you think this approach will still be valid in these circumstances where torsional modes are significant? So, Najun,
Okay.
any ideas on this question?
Here we go.
So first of all, thank you for the question. I think this is a very, very good question. So I should say, our code of practice, so it's for general cases. This is not designed for consider very, very exceptional case. So in normal cases, so I think the majority, maybe more than 95% of the true lateral load will govern the case rather than the torsional load. But there may be some very limited condition, as this particular audience mentioned. There may be torsional governed. So then come back to the original question. So for the updating of the 2019 code, so actually we consider both the complexity of the problem and also the scientific, how scientific the torsional rule can be used. So our current torsional load assumption is to consider that the torsional load is based on the calculation of the lateral force. So for the lateral force, we give an eccentricity, and this eccentricity is based on the geometry condition of the building. So then this eccentricity together with the lateral load will generate the equivalent torsion. This is a quite straightforward and a simple torsional force calculation. And as I mentioned, so this can cover the majority of the cases. But if in very, very rare case, if really the structure engineer, especially the RC, have a very big concern for the torsional governed case, so I think they may seek the advice from the BD or send a submission inquiry, or also even directly go to the wind tunnel testing to get the more accurate and scientific result. So I think that's my answer. So, but I think the question is very good.
Yes, and then maybe just supplement that. When a building is torsionally sensitive or dynamically measuring is significant, even in 2004 code, it's already mentioned that you have to have special consideration for the design. And in the new code, we actually given a quantified method to assess this criteria. And if the torsional component is such significant, then you actually will need to require wind tunnel test assessment.
Yes. So in this case, if you find that your design building actually may be torsional significant, maybe you need to consider to do the wind tunnel test to reflect the actual situation.
Yeah, and also I think maybe Alexis can further supplement. So I think maybe the structure designer can first, from a conceptual design perspective, to review. So why the first mode is a torsional governor, right? Because normally we think it's a lateral governor. So is there any way that the designer should further increase the torsional stiffness to mitigate that? So I think this may be another way we can think about.
Yes. True. Okay, so the next question is, should shattering effect be considered for the design of temporary structural elements such as hoarding? Oh, okay. This clause actually, I think the question is focusing on the 37% of the wind load. In this case, if 37% of the wind load is used, so any further benefits from the torsionality factor and the shattering effect actually is not allowed to consider again. But the topographic factor and the size factor, which depends on the the structural form and the location should be considered. Yes. So the next question is whether sheltering effect can be applied by buildings in the same development. Okay, I want to make clear that in the Appendix A2 of the code, actually the direct sheltering effects is to cater the effects of building from surrounding buildings around the sites, but not within the sites. So in this respects, so we expect that the direct sheltering effect actually comes from the building outside the site. So in this case, buildings within the same development, that means even Tower 1 and Tower 2, the effects of such sheltering should not be allowed. Yes. Okay, the next one, why do we need to consider torsional load in the new code? Okay, Alexis, please.
I mean, to just a very simple reply is that this is the real behavior of a structure. And over the years, with all the internal tests we carry out, and this is reflected in the result of the test. So we are just including something which is real into the latest scope for the design.
Yes. I think exactly as what Alexis mentioned. So we observe many internal testing results. Even it's just a square shape or rectangular shape, right? It's a very regular shape, but still we can. So the force balance, or the pressure integration, we can always measure the aerodynamic torsion. So I think the reason is because normally in the natural boundary layer, especially if the wind blows in a diagonal direction, so the distribution of wind pressure on the building surface is not uniform. So this non-uniform distribution of wind pressure very naturally will generate a torsion. So so our revision of the code just reflects the true behavior, the true aerodynamic behavior.
Yes. So I would like to suggest that with designer not to misunderstand that this torsion is to cater for the eccentricity between center of rigidity and the low center. This is not the case. Actually, the torsion in this code generate by the non-uniform wind load on this building. Actually, the gust wind actually is not blowing at the same pressure over the whole building. So remember, don't misinterpret this clause. This is in addition to the torsion we normally design due to the eccentricity of the low center and the center rigidity. Okay, so the next one is for me. Could we use the h/500 for checking limit instead of the acceleration check? Yes, designer can still use the h/500 deflection limit because it is deemed to satisfy requirements. But now with the new code, designer can choose either the deflection check or the acceleration check. So both, if the buildings satisfy either one, so it will be accepted. But bear in mind that for some buildings, with the acceleration check, maybe the static deflection is more than h/500. The building facade design, such as the glass, the curtain wall design, designer has to cater for such deflection during the facade design, because even the acceleration is okay, maybe the static deflection is quite large. It may induce some distress to the building facade. So if it's really this case, so you need to work with the facade design to cater for such movement.
Yeah. So to supplement Fei-Yong is, so our acceleration is just from the wind perspective. So that's purely for wind comfort. But if the designer can satisfy the acceleration criteria, it only means it satisfies the wind comfort part. But it doesn't mean that if the facade designer or the mechanical engineer, for example, the lift shaft, they have requirements for the interstory drift or total deformation check, that can be relaxed. That's not the case. It only says for human comfort, yes, that is okay.
Yes. So please alert this one. Okay, thank you. And then for the next question is in the Wind Code 2019. It is mentioned that torsional load case can be ignored if the maximum interstory drift due to torsion load is less than 25% due to the natural load. Does it mean that if I fulfill this requirement, I don't need to consider torsion in the load combination case 1 and 2? Okay, Lapsun, please.
Okay. Yes, I think this is the written in the COP. So in the COP, I think what in chapter 2.4, I think in the COP. So in the COP, it says the torsional loads always exist, as explained before. But in some particular conditions, we say the structure design is robust enough. So because of that, and in that scenario, even though we ignore the torsional load, but still the design is safe. So we give a series of exception criteria. So for the designer, if they can fulfill those conditions, so they can ignore the torsional load in the load combination. And one of the criteria, if we read the clause 2.4 more carefully, so that is to say, if the building is a torsional regular, so then the torsional load cases can be ignored. So what is the so-called torsional regular? So the torsional regular is defined if the interstory drift and the full torsion is smaller than 25% of the interstory drift at under the lateral load. So then we can define this as a torsional regular case. For this case, the torsional load can be excluded or ignored from the load combination case.
Yes, yes. I would like to supplement this a bit. Actually, that we have some exemption in the code to not to consider the torsion, which is listed in the clause 2.2.4 of the code. You may need to check A, B, C, D condition. If you fulfill one of them, you don't need to consider torsion. But for the item D, actually it's just an exemption of case 3. You need to consider the torsion in the case 1 and case 2. But for the other 3, A, B, C, actually the torsion actually can be totally ignored because we think that the building actually is torsion insensitive in this case. So that would be no case in this respect if the torsion is totally ignored.
We can reduce from 24.
Yeah, so the low cases will be changed from 24 to 8. But for item D, if only the case 3 is exempted, then the total number of cases would be 16.
Yes.
Yes.
That's right.
Thank you. So the next one is whether there are any simplified method for minor structures under the new code. Do we have? I think we have some we have some coefficient or clause for a fence wall. And
we
also have temporary structure for for cover walkway and some contractor check and cost 2.5.
Yeah, freestanding wall.
Freestanding, but we also have freestanding wall clause for freestanding wall. Yes.
I think in the clause 2.5, it has been expanded as such that it's not just used for doing the hoarding and cover walkway design, and it can be applied for temporary structures. So in my early presentation, you talked about when you're doing makia, bamboo shed, tents, that sort of thing, then you can apply the clause 2.5 to it.
Okay, thank you. And then for the next one, for a facade system such as curtain wall, how to determine the size of loading area for size factor? Is it the whole area or the area of a single panel? Okay, Lapton, please.
Okay. So I think maybe the audience who asked this question has already get some of the idea about how to calculate the size factor. So to be simple, the size factor related to the loading area. So related to the loading area. So then we can separate this into several levels. So for example, for a facade panel, so then the size factor need to be rely on the loading area of the facade. So that is the half parameter of this facade panel. So that is for designing the facade. And for designing the fixing of this facade, so then we need to consider the loaded area, this fixed support. So whether it is a quarter of the facade or 2/4 of the facade or 4/4 of the facade. So after we have identified that loading area, so we can calculate the half parameter length. And then on a further higher level, so we can go to like the secondary members or secondary structures. This secondary truss may support, for example, quite a few glass panels. So then again, so the principle is we need to identify how many glass facade panels this secondary truss or secondary structure supports. So then the size factor will be the half parameter of the loading area of this secondary structure. So it depends. So I think for Yong, the key point is the designer, the facade designer need to have a clear idea about different levels, cladding panel, the fixing of cladding panel, and also the secondary supporting members or structures of the cladding panel. What are their loading area or tributary area respectively? So then based on that loading area, they can calculate the size factor. And also bear in mind that this size factor, so on one side, it relates to the half parameter length. So that is the loading area. And also when they look for the curve, so which formula, which equation or which curve they need to follow, that also relate to the location. So where the cladding pressure are located. Yes.
Yes, thank you. So the next one is how is the sheltering effect analysis applied with the topographic significant sites? So I think this question may be a little bit confused between the sheltering effect and the topographic significance, because in the code, sheltering effect and topographic effect actually are considered in two separate factors. The sheltering effect actually is assumed that the sheltering is based on a flat ground. And although we have some explanation on how to take the level of the sheltering effect, but actually we assume that the sheltering effects is assuming the buildings are all on the same flat terrain. And then we calculate the reduction due to this one. And then for topography, the clause in Appendix A3 actually has taken into account the topographic factors. Actually, they are applied separately. Or any supplement from this?
Yeah. So I think exactly as what Fion explained. So in topographic significance conditions, the calculation of topographic impact and sheltering impact should be done separately. So they are separate. And for the topographic calculation, just refer to the appendix. And for the sheltering calculation, I think Alexis has already given a presentation in the previous PPT slides in the slope terrain, how to calculate the sheltering effect. So then just follow that rule shall be sufficient. Yeah.
Yes. So thank you. And then the next question is, when calculate the torsional load, should the along wind be scaled up due to a crosswind effects? Okay, so maybe I talk a little bit and then Lieutenant, you supplement. And for calculating the torsional load, actually is based on the along wind. The along wind loading multiplied by the eccentricity depending on the building shape. And then with this case, the crosswind is not necessary to it's not used to calculate the torsional load. When we will use the crosswind, actually is we need to calculate the crosswind total base moment and compare against the along wind total base moment to decide whether scaling factor or wind tunnel test is required to calculate the WX1 and WX2 in the table in the 2.2.4. And for the torsional case, we just need to use the along wind force to calculate the torsion. Yes. Okay, I think thank you. Then we shift to the next question. Is how about the sheltering effect provided by buildings on downhill side and uphill side? How is it calculated? So I think this actually is covered by the PowerPoint. As I mentioned earlier, we assume that the sheltering effect is assessed assuming that the buildings are on the flat terrain. But in such case, how we take the building height for estimating the sheltering reduction HD, we need to be on the conservative side. So in the code, we actually has used a more conservative approach to interpret the building heights of the building, of the surrounding buildings, in order to to be more conservatively to calculate the the reduction due to sheltering effect. So you may refer to code EN. I'm sorry. You may actually the graph in this PowerPoint is on page A2 of the explanatory notes. You may refer to this diagram to determine how to take the building heights of the surrounding building if it's on an uphill or downhill situation. But this is not to take into account the topography effect. Actually, this is just to be on conservative to consider the sheltering effects. Okay, so the next one is for wind torsion. We can use the transform shape based on 4.2.4. But how about the across wind moment? 4.2.4. I'm sorry, I need to.
I think they're talking about
enclosing.
Yeah, enclosing.
Oh yes. Yes. Maybe I answer this question first. Actually, 4. Oh, okay. The last two questions. May I?
Oops.
So for. Yeah, I think they talk about this one.
Oh yes. 4.2.4 actually is talking about how to calculate the pressure the force coefficient of a building, and then for this case, we actually show a lot of examples of how to calculate the B and D for this case. And then you may need to note that this B and D is also applicable for calculating the torsional load. But this case actually is not the B and D for calculating the across wind. It's not the enclosing rectangle. Maybe Natuni supplement a bit on this.
Yeah. So I think the audience may be interested to get a clarification. So when to use 4.2.4? Yeah, as Feion explained, so 4.2.4. So first of all, it is used for calculating the force coefficient. So that is for a long wind calculation. And secondly, they shall also be referred for calculating the torsional load, and that's all. And for the across wind base moment calculation, so we need to refer separately to the chapter 2. So within that, it has already defined for calculating the crosswind base moment, we shall use the smallest enclosing rectangle.
Enclosing. So can I say that for some cases, the rectangle for the B and D for across wind actually is not the same for the B and D for the force coefficient and the torsion?
It's possible. Yeah,
yes. Okay, thank you. So the next question is, in the code 2019, topographic factor is calculated with Z rather than H. Does it mean that for the same building, we have different topographic factor at different heights? Is it acceptable to use building height H for the full height? Yeah.
So yes, they need to calculate the topographic factor at the different levels, but the next question is, can they use the total building height for calculating the topographic multiplier? The answer is no, because if we look at the counter plot curve in Appendix A for the topographic multiplier calculation. So actually, we can see the higher the building relatively to the hill, the smaller the topographic impact. So that means if we use a higher height, we will calculate to obtain a smaller scaling up factor, a topographic multiplier factor. That is on the unconservative side. So that's why it is not so acceptable.
Yes. Okay, thank you. So because of the time is running out, this is the last question. And so what is the definition of usual shape of building for the requirements of wind tunnel test? Actually, it's a very, very, very difficult question. and actually it happens since we have the wind tunnel test technology. Because currently we also encounter such question, but in the 2008 we specified that usual shape you need to do the wind tunnel test. So may I invite Neptune to elaborate more about on the usual shape of the buildings?
Okay, so so the so-called Euro shape actually is in the initial judgment. So whether the standard approach applies or not. So for this initial judgment, actually, regarding the definition of a Euro shape, so we follow the same principle as, or the same definition in the 2004 wind code. So that means, based on the old code, if the judgment it is a Euro, so then we can still follow. But I think what we make further progress compared with the 2004 code is because, as Fion mentioned, we have a further progress regarding the wind tunnel testing. So then we have some more data to support us to give some further force coefficients or guidance to calculate the force coefficient. For example, we have already added the L shape, the Z shape, U shape, Y shape, or X shape. So I think this is more comprehensive compared with the 2004. And also we gave some further general rule if that falling outside. So how you can use a rule of thumb to roughly get an equivalent rectangle. So I think those rules they can follow. But if they have searched all those rules and still cannot find a proper shape, so I think then definitely they have to go to the wind tunnel test.
Yes, yes. So I would suggest designer to check the EN. Actually, in the code, we have a number of building form with suggested force coefficient in this respect. And also we have in the EN, we have some general principle of how to apply the enclosing rectangle to consider as usual shape. But in this case, I think all in all, we consider that the aerodynamic flow across the building is a smooth one without a lot of water shedding and also turbulence effects. So in this case, if there is a building with a very significant water shedding then it may be probably an unusual shape. Can I interpret in this way?
So for our code, so when we do the code drafting, so our except for the circular shape, so for the force coefficient and also for the crosswind-based moment, we try to get an equivalent rectangle. So I think that's the principle. But if really there's a shape, the aerodynamic behavior, so including the dynamic behavior and also the aerodynamic crosswind response, if they are too far away from the concept of so-called equivalent rectangle, so then definitely that will be the angular shape.
Yes, yes. Thank you. Okay, that's the end of the briefing section today. Thanks for staying with us until now. I hope the briefing section and the Q&A section help you understand more about the code. The grace period will end of March. So starting tomorrow, please grab your code and try on your current projects to try to understand more, because the best way to understand a new code is to use it, not just attending seminars. So if you have any further question on the code, send me an email at the following address. Yes, we are happy to answer your questions. Yes, thank you for coming. Thank you. Goodbye.
Thank you. Bye-bye.